let's have a look at some more rate equations and see what light they can shed on a reaction mechanism. Okay, so here we've got the reaction of ethanal. There's ethanal there with the aldehyde group there. It's the aldehyde group, and it's a dimerization reaction. That means one molecule of ethanol reacts with another molecule to join one big molecule here. Okay, and I've colored them in red and black so you can see where these atoms have come from and so forth. Now, if the mechanism was very straightforward and all that happened was one red ethanol collided with one black one, you would expect the rate equation to be rate and it would be second order with respect to the ethanol. Why would it be second order? Well, because the ethanol has got to collide with itself. If you double the concentration of ethanol, you don't just double the likelihood of collisions; you quadruple them. So that's what you'd expect if it was just this red one colliding with this black one, and that's not what happens. Because if you look at the rate equation is right. It is first order with respect to the ethanol. And a little bit strangely, it may seem, it is first order with respect to hydroxide ions. And hydroxide ions don't even appear in the equation. But what this does show us is that an OH minus has got to collide with the ethanol and react, and that's going to be the slowest step in the reaction, the rate determining step. The fact that OH minus doesn't appear in the chemical equation, but does in the rate equation, tends to suggest that the OH minus is a catalyst. So you need it, but then it gets regenerated later on. So with bearing that in mind, we'll have a look at what is thought is to happen, what's consistent with that rate equation. Okay, so, and again, you do not need to know this mechanism at all, but you can probably understand most parts of it. Also, interestingly, this did appear in a past paper about 10 years ago, but they gave you the mechanism and you just had to say which step was the rate determining step. So we've got 3 steps. We've got 1, 2, and 3. Which one is probably going to be the rate determining step? So in the first step, the OH minus has reacted. First step, the OH minus removes a proton from the black ethanol molecule to form this species here. Okay, this has got a negative charge on the carbon up there, and that will make that carbon a nucleophile, and that is going to, in the next step, that is going to do nucleophilic attack on this carbon here. Okay, so in step 2, that happens and you form this intermediate. And in step 3, this has got a negative charge on the oxygen. It's a strong base. It removes a proton from the water, and it forms the final product, and it regenerates the catalyst. So hopefully you can see there that the only possible candidate for the rate determining step is this one, number 1, and that's because it's the only one which involves the 2 species in the rate equation, the ethanol and the hydroxide ion. So that is going to be slow, and steps 2 and 3 are going to be much faster. Okay, let's look at another example. Oops. Right, this time we are looking at the reaction of propanone here with iodine. Now, if it was a pretty straightforward reaction, you would expect this to be rate concentration of propanone, first order with respect to that, and first order with respect to iodine. If an iodine molecule simply collided with a propanone molecule, that's what you'd expect. Now, when you look at the rate equation, you don't get that at all. You get, let's write it down here, do it in a different color. You get rate is equal to, right, it's first order with respect to propanone, but iodine doesn't appear in the rate equation. And it is first order with respect to hydrogen ions. I'll tell you, I'll put the iodine in there, but it is 0 order with respect to iodine, so it doesn't matter what you do to the iodine concentration, it doesn't affect the rate of reaction. So what we would say then is it would appear to be the rate determining step has got to involve H plus ions and propanone. Also, the fact that H plus doesn't appear in the reaction equation would tend to suggest that this H plus is acting as a catalyst here. Right, so let's look at the proposed mechanism, so we can work out which step could be the rate determining step. We've got 3 steps. We've got 1, 2, and 3. Okay, so what happens in the first step is you protonate the propanone and you form this carbocation intermediate here. In the second step, number 2 here, you deprotonate, you form this pi bond and you deprotonate the carbocation and you form that intermediate. And in the third step, which I haven't shown, this reacts with the alkene reacts with the iodine to form the final product. Now we know that this can't be it. This cannot be the rate determining step because you need iodine for that. So if that was a slow reaction, increasing the concentration of iodine would speed it up, and it doesn't do anything. Step 1 or step 2 could be the rate determining step here. Step 1 could be because it involves the collision of an H plus with the propanone, or step 2 because in order to form this carbocation, you need, what do you need? You need H plus and you need propanone. So the formation of the carbocation is dependent on both of those 2 things, and it actually turns out that step 2 here is the rate determining step, not step 1, though you could be forgiven for thinking it's step 1. But what you could say is it definitely can't be step 3.